right, everyone, so we're back now looking at beyond hypothesis testing. But don't forget, even though we're going to jump into new chapters, 9, 10, and 11, I'm going to give you all three at once. I'll explain in a second. There is always logic to my madness. But think about hypothesis testing. We do have our 4 steps. Everything that we do beyond this, in terms of the t-test, the ANOVA, the CHI, the Pearson, all of them always follow the same 4 steps. Because research has to be ethical. It has to be able to be duplicated, be able to be generalized. So to keep that flow, we always have to follow the 4 steps of hypo testing. So right, state it, set it, compute it, decide it. So I'm going to leave them up there just as a reminder. But before we can jump into the actual t-test, like T and Tom, we have to remember the z-test, Z and zebra. So first we have to think about the difference between the two. So we have the one sample, Z test, and we're going to have the one sample T test. They pretty much look the same because they kind of are. A nickname for the one sample T test is the approximate Z test, because in reality, what happens when you actually present something new onto the population? Theoretically, everyone's taken an IQ test. Yes, we know not everyone's taken an IQ test. When I ask my students all the time in class and I say, okay, who's taken a real IQ test? Like one person raises their hand. But theoretically, we've tested enough people in the population to know what the results are in terms of people's IQ. So we have enough information to actually gather and create a sampling distribution. A sampling distribution, as we've learned before and throughout other chapters, is a special kind of population. Instead of collecting individual raw scores and their tests, we actually think about collecting groups of people, samples. And enough sample groups will actually lead to a normal distribution. So theoretically, although the entire population has not been tested, we've tested enough sample groups to know what the population's reaction or intelligence, IQ, right, could be. So we actually leads to a normal distribution because the mean will always balance itself out. And so when we're talking about the z-test says we have a lot of information. And the t-test says we don't have all that information. So what do we do in that case? So for example, a lot of information means we have a couple of things. We would actually have the mu, the mean of the population. And if we have a real mean of the population, then we can actually calculate the real standard deviation of the population. But what happens when we actually have to estimate the mean? We don't really know what's going to happen in the population. So think about the time that we introduced the first time a cell phone, especially a touchscreen cell phone. So now the touchscreen has become so normal. For my son, for example, my son, when he looks at the baby monitor, he tries to pinch it. My Mac, he tries to pinch it and like open the monitor because he assumes that everything is touch. But in reality, at that point, for him, it's a norm. Everything is going to be a touchscreen. But for us, older generations, touchscreen is still something fairly new that we're still getting used to. And for older generations like my parents, it's really difficult for them to understand how to use it. So then, think about that. Right now, if we were talking about toddlers, my son who's 3, no problem, my teenager, my 14-year-old, all the kids that are younger generations, for them, using touchscreen is the norm. So we could actually get the mean of the population and calculate a real standard deviation. But what happens when we first introduced the touchscreen years ago? So we could theoretically estimate the mean, right? The mean could now be theoretically estimated by who? By M. And what is capital M? The sample. So enough samples of people, we could estimate the mean of the population. In other words, what would be happening with the population? But you can't take a guess to create another guess. That wouldn't make any sense. So the only thing that you can have is an estimated mean, but you cannot derive a standard deviation. You're not able to actually get it. So if you don't have enough information, then you can't run a one sample z-test. A one sample z-test requires a lot of information of our population that in reality might not be accessible, especially in times you introduce a new product onto the market. You don't know how others are going to react. So in reality, you have to then move on to what we call the t-test. And there's the one sample t-test that has some of the same assumptions as the z. For example, you have to make sure you have a normal distribution in order to run this actual test. Then you have to have the mean of the population. and you're going to run samples, and you're going to go on to run your hypothesis testing and test if there's a significant difference between, once again, that sample and that general population. But the advantage of the t over the z is the fact that it requires less information. So in reality, we're going to use an estimated standard error. So the standard error of m that we use in this one sample z-test is now going to become the estimated standard error of m, right? And so to run this test, we have to think about some of the requirements that we're going to need. So because we're looking at samples, remember when I had told you guys before in the other videos that in setting the criteria, we have something called degrees of freedom. And I said this is going to come to play now when we go beyond the one sample z-test. In the one sample z-test, all the information we had was already known of the population. So in reality, although we were testing samples to talk about populations, all the information is pretty much known in terms of the population. You're just going on trying to see if you can reinvent the wheel. In the t-test, you're not reinventing the wheel. You're introducing something new onto the market. So you have to keep in mind that the sample is going to be restricted. So if the sample is restricted, this is where the idea of degrees of freedom comes in. Or what I had put up there in previous videos as DF, right? So just in case, standard error of m, this is the one that goes there. Estimated standard goes to the t. And now we're talking degrees of freedom that also goes to the t-test. So degrees of freedom is how many of the actual values are free to vary. So the example I give most of the time to students is simple. The sample has to be restricted. You can't ask black people what they think and then ask white people. You can't ask white people what they think and ask white people. You can't ask Latinos what they think and ask Asians. That really wouldn't make any sense. If you want to know what someone thinks, ask people who are just like them what they think. In other words, the sample is restricted, meaning that it must represent the population that it comes from, and not just common sense. So for example, if we look at some numbers, let's say we had 4 random values. And when we add up these values, right, this is sigma lowercase, means add them up. When we add up these X scores, or these raw scores, let's say the total came out to be 20 points. So adding up these numbers comes out to be 20. If we do a random number, so my camera guy, what's a random number lower than 20? 6. Give me another one. 10. One last one. 2. Okay, great. Does anyone know what this last number is? 10, 16, 17, 18. What is the only number that this one could be? 2. It can only be 2 to make this equation true. So in a sample size of 1, 2, 3, 4, how many are free to vary? Only 3. 3 numbers can be whatever they want, and the last number is stuck. So in other words, in a sample size of 4, degrees of freedom tells us n minus 1. In other words, 4 minus 1 equals 3. 3 numbers can be whatever they want because the last number is stuck and has to be 2 in order to make the equation true. So in other words, if you were collecting a sample of population, you had 20% black, 15% Hispanic, and a 30% Asian, you had to make sure the same percentage and breakdown is within your sample. Your sample should look like your population. If not, your sample doesn't actually represent your population. So this is where degrees of freedom is going to come into play, because we have to make sure we account for a mathematical equation to account for the fact that our samples are restricted because they need to represent our populations. And so going into step 2, setting our criteria, it's not just the alpha level, it's not just the critical region, it is also now degrees of freedom. Keeping in mind that the sample size is restricted and all these values are going to be needed to actually find the actual critical region. The number that tells us where the tail starts, the number that tells us where the area of significant, extreme, different starts. Where you need to be to actually find a significant difference.